Hello friends, welcome to today's class of ANN. So I'm your professor Vinay Sangoli. Moving ahead. So in the previous class, we have seen your one of the very important algorithm called as steepest descent algorithm, right? What all did we see in your steepest descent algorithm? We came across some things in your steepest descent algorithm wherein we were calculating your gradient. We are calculating your gradient and we came across your gradient of error, that is epsilon, right? Then using that epsilon, we calculated our weight updation, that is W of k plus 1. Then that gradient is multiplied along with your learning rate to get your updated weight. That means you can say in steepest descent, our whole algorithm was working based on your exact gradient information. And this is obtained by only when we define our data sets completely in advance. That means it was a classic example of your supervised learning. Whatever was the supervised learning, using that, first we used to define all our data set, that is x of k, and then we would go ahead with calculation of your weight updation. And while calculating your weight updation, we were using our gradient information. Right? So up till here it is clear, I guess. Then you might have also come across that we were calculating our R and P. We are calculating our R and P. I hope all of you remember your R and P. So friends, before I move ahead with further with this video, please make sure you have watched the previous video, or else it would be a bit difficult to understand. Right? Now, what we did there, we also calculated your R and P. So what is R then? R was nothing but your, anybody? It is autocorrelation matrix. And what was P? P was nothing but your cross correlation matrix, right? So based on that, today we will see a new algorithm called as mu LMS algorithm. We have already seen alpha LMS. From alpha LMS, we came to a gradient descent. From gradient descent, we are coming to a mu LMS. Mu LMS. Now what is this mu LMS? Mu LMS is nothing but it is an approximate gradient descent calculation algorithm. So that means the calculation of the gradient would be the case when the data sets are approximate. So I mean to say your R and P are computed. How they are computed? They are computed assuming that you have a true gradient. That is, the gradient is obtained by, say, when the data set is completely specified in advance. But there could be a case wherein your R and P cannot be computed very accurately. So when this case would arise, when you have a random stream of patterns. So remember friends, calculation of R and P accurately is very important. And how you calculate accurately R and P? R and P can be calculated accurately only when your data sets are completely defined in advance. But there could be a case wherein your data set cannot be defined completely ahead in advance, and they may be random in nature. That is, they cannot be a you can say they cannot be specified in advance. They could be random. That means in I am trying to say that they are drawn from a stationary distribution and not from an accurate distribution. In that case, your R and P cannot be computed very accurately. So that means you can just observe here, your R and P can be computed exactly at every iteration k, provided your true gradient, that is del of epsilon, is obtained using R into W of k minus P. This equation we already seen in your previous algorithm. Now what would happen now? For random streams of R and P, your calculation will not be accurate, as I explained till now. Okay, so what we would do in such a case? In such a case, we will try to get the nearest values and need to observe the data for a large period of time and then take their averages. So observe here friends, first you need to take the nearest values as they are not accurate, then we'll observe it for a large period of time. Observe it for a large period of time, it means that what now? Will not take only one iteration, we will take n number of iterations. After taking n number of iterations, we'll go and take the average of those values. So we don't know how long to examine the stream of these reliable data sets, that is R and P. So therefore, we, in order to overcome this difficulty, we will be using your epsilon of k. In the previous case, we were using what now? Only epsilon. We are using only epsilon. Now what we'll be using? We will be using epsilon of k. So I hope you are getting here. So this is your epsilon. We used this in your previous algorithm. Now we will be using your epsilon of k. That is, this epsilon of k is nothing but it is a value which is observed over a large period of time and then whose average is taken, which is nothing but your epsilon of k. Okay, so I hope this is clear. Now going forward, in order to get this epsilon of k, we'll go ahead with a small gradient which is del tidal of epsilon of k. Now this whole thing is nothing but your mu LMS algorithm. Remember friends, the previous steepest descent was working on epsilon. Mu LMS is working on epsilon of k. That's all, very simple. Now what is this del tidal of epsilon of k? It is nothing but again a differentiation of your epsilon of k with respect to omega of k. What is del epsilon? Del epsilon was nothing but it's a differentiation of your epsilon with respect to weight. And what is del epsilon of k? It is again differentiation of epsilon of k with respect to omega naught of k. That is the only small difference. Now here what we'll do now, we can remove your e of k outside. So that if e of k is removed outside, then we'll get the second equation which I have written there. Then finally we'll be getting your del epsilon of k, that is del tidal of epsilon of k is equal to minus of e of k into x of k. So this equation is very important friends, and hence we take it as equation number 1. Now from here moving ahead, you already know what is your e of k. You already know your x of k. What is x of k? X of k is nothing but the input patterns. What is e of k? E of k is nothing but the error patterns. Okay, so we'll move it with the next slide. Yeah, so you already know your e of k. What is e of k? It is nothing but d of k minus x of k, that is estimated, that is what you have got minus the what you already have. Okay, this equation we already seen, that is e of k is equal to d of k minus x of k, and you already know what is s of k. S of k is nothing but x of k transpose into w of k. Now we'll go ahead and define your update equation in your mu LMS algorithm. So what was your update equation in your steepest descent? I hope you remember the steepest descent updation algorithm, updation equation. It is nothing but if you try to recall it, it is very similar to our equation number 2 which you are seeing right now. Only small change we have done here is your del tidal of epsilon k. That means instead of epsilon we will be using del tidal of epsilon of k. Okay, now we'll go ahead and substitute this epsilon of k. What is epsilon of k? From your equation number 1, it is minus of e of k into x of k. So the minus of minus would get cancelled. You would get eta e of k into x of k, which is our equation number 3. You already know what is your e of k. Here you can see you already know your e of k. So you substitute the value of e of k, which is nothing but d of k minus x of k into x of k. Now what we are doing then? We are trying to change our whole updation equation, which is nothing but w of k plus 1 is equal to w of k plus eta into d of k minus s of k into x of k. Now the next big question arises is, when does this equation will converge? When does the average of this delta of epsilon of k will converge? So in order to do that, what we'll be doing is we will be applying our expectation. So next step is nothing but keeping the weight vector fixed and taking the expectation on both the sides of equation 1. So you already know what is your equation 1. It is nothing but your epsilon of k minus e of k into s of k. Okay. Yeah. So to make it more visible, I have increased the brightness. So moving ahead, what we'll be doing next thing? We need to substitute the value, that is we need to take the estimate of your equation number 1 on the both the sides. Okay, so I have taken the expectations here. So taking the expectation, what you will get, the next step, the next very important step is, after taking the expectation, you can go ahead and change your values. Okay, so you can see here I have taken the expectation. After taking the expectation, you will get the next very important equation, that is you will be substituting the value of e of k. Okay, so what we'll do, we'll substitute the value of e of k and we will get our equation number 6. You can observe here. So I substitute the value of E of k, which is nothing but D of k minus X of k transpose into W of k. Okay. So then after that we can simplify this equation. We'll be multiplying your X of k along with your, so this is the substitution in place of E of k, that is in place of E of k. Then what we have done, we will be multiplying your X of k and D of k is multiplied, and you will get D of k into X of k and so on. Okay. Then what is the next step you will be getting here? We will be applying expectation to only your inputs and expected value and not for weights. I hope you know this already from the previous equation. Okay. Now what is D of k into X of k? It is nothing but your P. What is X of k into X of k transpose? It is nothing but your R. So you have got your RW minus P. And what is RW minus P? It is again nothing but your del of E. So please observe this, friends. What we have done, we are getting del of E, which is equal to expectation of del tidal of E of k. That means this equation is trying to tell us that when we take long-term average of del tidal of E of k, it would reach your del of E. That means we can easily use your del tidal of E of k whenever you have an unbiased estimate. Whenever our estimate is not clear, in that case we can use our del epsilon of E of k. Then how do you obtain this del epsilon of E of k is the next question, right? So how do you obtain this del epsilon of E of k? We will be go on collecting our del epsilon of k for a large number of iterations. That is, we collect your del epsilon of k up till say n number of iterations, then we change the weights for all these iterations. Thereby we will be getting W of k plus 1. Now, next very important thing is how this del of E can be calculated from del epsilon k tidal for all values of X of k. But what is the one challenging thing here? Our X of k is not already defined. I mean to say it could be a pattern which is random and which is drawn from a stationary distribution. Okay. So therefore here is what your mu LMS is very important. That is when it is random and it is not defined clearly. Okay. So whenever we have such a case, and when you have a deterministic case, what you get is you'll be getting your, so please try to observe here, whenever it's a deterministic case, your eta will what? It will reduce. That is, eta is kept small, and your change in weight, which is nothing but W, will also be small. And whenever your change in weight will be small, therefore we can say your W will remain constant over n number of iterations. That means your Q is the number of patterns in the training set. So therefore we'll move ahead to the next slide. So this is how your change in weight, which is nothing but delta W, is given by. That is, delta W is equal to minus of I is equal to 0 to Q minus 1 del of Ek plus I divided by del of omega k plus I. So rearranging the terms, that is here we have multiplied and divided Q is multiplied and Q is divided. Then after that, that is in equation number 10, you have multiplied and divided Q. Okay. And after rearranging the terms in equation number 1, in equation number 11, we'll go ahead with your equation number 12. This is what we'll get. So you can see here, the change in weight is nothing but it is equivalent to the epsilon divided by your differentiation of W of k. This epsilon denotes here nothing but your mean square error. Now, that means your weight updation always follows the true gradient provided you take the average of your whole output. That means your del epsilon of k with tidal is an unbiased estimate of del of E. Therefore, we say that your mu LMS will search the VNR solution for any given outputs. That is, since your del epsilon k is an unbiased estimate of del of E, we can expect your mu LMS will search the VNR solution. Okay, I hope friends this is clear. Then only small point I would like to express at the end. What is one difference then? Your alpha LMS also uses gradient information, but it will search out the VNR solution only for the normalized training set, but whereas your mu LMS is working for all the other training sets. I hope this is clear, friends. So here we finish our our algorithm, which is nothing but M LMS algorithm. Okay, so I hope it is clear. If you have any doubts, you can always call me or message me on my WhatsApp number. Thank you.